Hello and welcome to the stream. The last two times, or last three times, we built an infrastructure for CPU, and we built an infrastructure for testing the CPU. So what we have is, generally speaking, switch case for handling each and every opcode, which only a few opcodes already implemented. And we have a test program, which looks something like this. Which sort of exercises each and every opcode that the CPU has. And we convert that into a memory image that is suited for the CPU we're implementing, that places in memory each byte that needs to be in memory, so it initializes the memory. And last but by no means least, we have this. This is the test plan. It lists which address the CPU is supposed to read from, what data it's supposed to read or write, and whether this is a read or a write. So this lists cycle by cycle everything the CPU is supposed to be doing. What we also have is let's just split here. And okay, what we also have is the verification code, which reads in the memory image, puts it into the memory, reads in the test plan, and then starts executing the CPU and making sure that what's executing is what is supposed to be executing. Okay, so let's begin. And when we begin, we can just compile this and run. And what we get is system error because I did not provide it the files it needs. So we will go to the history, and here we go. We run the verify CPU program. We're telling it, this is your test program. This is the test plan. Go. And what it says is we got to line 7. So the first 6 cycles are running correctly out of 9,581. So we're pretty good. And what it says is that cycle 7 is incorrect. It was supposed to read from 6F9. Sorry, it's supposed to read from 6F8, but instead it read from 6F9. And what we need to do now is fix the opcode that is misbehaving. So what is this opcode? The last opcode we executed was, we did transfer XS, and then we did load A start, and sorry, transfer XS, it's a bit hard to see because it's not clear when we're executing and when we're just reading. Later versions of the 6502 had a bit saying exactly that, whether we're executing, reading the opcode or just another read. This doesn't, so we need some context. We do transfer XS, and the problem is that we move on to the load A too soon. We were supposed to take 2 cycles, instead we're taking 1. So let's see. Transfer XS is opcode 9A. Opcode 9A is here, and we have two functions here, the actual transfer and the implicit address mode. So we don't have a text file, so just let's fix that. So the implicit address mode was actually supposed to waste a cycle. So let's do that. We go read PC and then we return the PC. And now, if we compile and run, we see that we reached cycle number 10. So we got a lot further. So the rest of this live stream is going to be like this. We're going to run the code, see where it got, see what the problem is, and then try to fix it. So quit now if that's not what you came here to see. Okay, cycle number 10. We were supposed to do push A, but that's not an implemented opcode, so I doubt that would work. Push A is opcode 4.8. 4.8 is implemented. So let's see what the problem is. Read operation where write was expected. Expected 1, got 0, 1FF, data 3. Okay, so we were supposed to write, and we were supposed to write to read operation where write was expected, plan line 10. I think we're even off by 1 because this is the write. So we were supposed to write to 1FF, and instead we are reading from 1FF. So let's see why that is. I think I know why that is. So let's see where the opcode begins. The opcode begins here. So on cycle number 9, we go, we read the opcode, we read the one next, and then we go 1FF right. So that's the push A. And by this point, we're continuing on to the next instruction. So let's see that in Visual 6502, because it does give a better representation. So we want the advanced mode, and we'll scroll this up so we can see the backtrace. And now we want the opcode to be 4.8. And now we can actually see the execution. So first cycle is read of the push A, and then the second cycle is a read from the next program counter, and then we have a write to the stack pointer, and that's it. Okay, let's see what we're doing. And for what we're doing, we can actually use a debugger. So verify CPU. And let's break on the bus operations. No, let's break on op PHA. And now we can, no, sorry. Let's run it with the correct arguments. Okay. So let's break on op PHA, and now we go run. Whatever. So for op PHA, we perform a write to ADDR, which is one FF, as it should be. So that should work. Why doesn't that work? I think we have a problem with the error message. I think the error message is incorrect. Read operation where write was expected. Yeah, that's incorrect. Write operation where read was expected, and this is read operation where write was expected. I think now things will be clearer. Write operation where read was expected. Expected 1 got 0 on line 10. So this was in fact line 10. Sorry about the confusion. And at this point, it was expecting us to already be here. So something isn't taking the correct number of cycles. And what is strange to me is that we actually reached this point. So it means 9 was correct. So let's look at the visual execution again. First cycle, it's supposed to take 3 cycles. The first cycle, we read the opcode. The second cycle, we read from the program counter +1. And then the third cycle, we write to the stack. And that is precisely what is described here. First cycle, we read from 6FA. Second cycle, we read from the one right after that. And we don't do that. We immediately go here. Okay. So, op PHA. If you see a problem I don't, then feel free to comment. ADDR mode stack does a read of the PC. So that should produce the extra read. Okay, I'm going to do. I'm going to make things a little clearer. We'll log everything we actually do. So we have the cycle number. We don't have the cycle number. We'll keep the cycle number. Start gray cycles. Cycles until start. Size t. Cycle num. Okay, so what we do is cycles until start and cycle num equals 1 because we want to match what the test plan is saying. And then we go if cycles 1, then we go std cout read. Let's print the address, which is address, yeah. So print the address and print the result, which is ret. Right, and also print the cycle num. And if we do a write, we go the same thing. We print write address value. And now if we run everything, it should be easier to see. It converted to character, so because it was a single byte. Okay, so now, and we need to advance cycle num. Okay, so we see that we are on cycle number 11. We are writing to 1FF value 3, which is exactly what we were supposed to do. Yeah, I think that's a bug in the test plan somehow. What that is, line 10, write operation where read was expected. Test plan 0. Okay, there's some bug here. Let's go to check and put a breakpoint on verify CPU line 83. Okay. And now if we go up, we can see what test plan says. And test plan, that's not what we're looking for. Says 1. Okay, I'm a bit baffled here. I'm sorry this isn't flowing as it's supposed to, but we have something wrong with the infrastructure, because we obviously see that. Let's print everything. Test plan 0. Test plan 1, test plan 2. Sorry about that, but this is actual live coding, so I'm actually trying to figure out what's wrong. And it says A9 6FB. What is A9 6FB? We didn't advance. Why didn't we advance? We didn't advance because we didn't advance. We really didn't advance. Okay, so valid. If valid. Oh, okay. We got further. Okay, sorry about that. Okay, unknown command 40 at 7:01. This is where this method really begins to show its merit. So, command 40. We can just look here for command 40. We know it's line 22, and this tells us that this is return from interrupt. The RTI means return from interrupt. So we don't even have to go to the data sheet to know what instruction it is, because it's in the source program of the test program, and we have that printed in the test plan. What we need to do is to go to the data sheet in order to see what that actually means. So if we go to RTI, which is here, return from interrupt, we see that it affects all of the flags, and it doesn't say what, it doesn't list it here. So we can do it here, but I'm not sure we have to. But let's do it anyway. Return from interrupt, and we see that, as always, the next cycle reads the next instruction, always, because this read happens before the 6502 even had a chance to... I think my image is frozen. Can you see me? Can you? I'm going to reset the streaming first. No. Okay. Say something on the. Say something if you can actually hear me. Okay, cool. Then my feedback is shot, but if you can see me, that's fine. Okay, so what I said is the next cycle after the fetch will always fetch the program count, the memory location after where the opcode. Always. The reason is it happens before the 6502 had a chance to analyze what it was fetching. So that happens automatically. For most opcodes, that's what needs to happen, not for all of them. So, okay, RTI, that's useless, but fine. And then we read from the stack pointer, from the stack. Everything starting with 0, 1 is the stack on the 6502. We read a value. In this case, we read AA. And then we read 0, 0. Fine. And then we read more 0, 0, which is, okay, bummer. Because now it's more difficult to see what happened. What happened is that this is a dummy read. Let me just scroll this up. This is a dummy read. And then what happened is that the status was supposed to get. Okay, let's reset this and set up the stack a little better so that we can understand what's going on. So let's do 1, 1, 2, 1, 2, 1, 3. And now let's set the stack. The stack is FD. Okay, that's fine. That's fine. Okay, so first cycle we fetch the opcode. Second cycle is dummy. And then we fetch 1, 1 from the stack. We fetch 1, 2 from the stack. We fetch 1, 3 from the stack. One, two, three, 1, 2, 3, 4, 5, 6. And then we jump to 0, 0, 1, 3. Yes, that's my bad. Okay, let's set up the stack again with 1, 4 at 1, 0, 0. That will make things clearer. Okay, so first opcode first cycle we fetch the opcode, second cycle is dummy. Third cycle may not seem like that, but is also dummy. The reason is at this point the stack pointer is pointing to a free location on the stack. So it's fetching a value, but it's not doing anything. It needs this cycle for the ALU to add 1 to the stack pointer so that it can fetch the next value. Next one is 1, 2, and then 1, 3, and then it wraps around, but it doesn't care. 1, 4. And now what we see is that it jumped to 1, 4, 1, 3. So 1, 4, 1, 3. And if I just continue this, the status flags. Okay, let me make it clearer. Let's reset this again by making this FF. And I want you to watch the flags, the CPU's flags. So again, first, second, third, that's dummy. We fetch FF, and then 1314, and we jump to 1413, and we were supposed, not sure why that didn't happen, we were supposed to get the flags all set high, because obviously I placed this in the wrong place. Sorry. So let's put here 1 as before, but here put FF, and this should make things clear. Sorry about that. Again, fetch opcode, dummy, fetch the flags, and then now look what happened to the flags. They're all set. So what RTI does is it fetches a value and put that in the status, and then it fetches a value and put that in the low part of the program counter, and then it fetches a value and put that in the high part of the program counter, and then it just continues execution from there. So that's the 6 cycles of RTI. That was a difficult one. Okay, let's see how we code that. So first thing, we need to put that in the right place. So case 40 op RTI ADDR mode stack. I will always overshoot, always. Okay. 6502 op RTI ADDR. Cool. And we will need to declare the function. Op RTI. I keep them sorted so that they're sort of reasonable to find. Okay, what do we need to do here? So first of all, if we compile this as is, we will no longer throw the assert that says we don't know the opcode. Instead, what we will have now is that we're violating the test plan. So on line 24, we were expecting to read from the stack. So notice how far we got. We read the opcode correctly. We read the memory address after the opcode correctly. And then when we were supposed to read from the stack, that failed. So let's do that. We go read from, that's the address we got actually. And while we're doing that, we go reg stack pointer plus plus. I'm not talking about this, but I'm trying to keep this the same order as the CPU does. So the CPU first initiates a bus operation with the information it already has, and then also sets up internally to update the internal state. And that takes time, and that's the reason for the dummy cycles. Okay, so if we do that, we should get to cycle 25. There you go. Cycle 25 says read from wrong address. It was expecting a read from one FD, and instead it got whatever, which makes sense because we didn't do anything here, right? So next we need to read from, we need to compose reg sp with 0, 1, because that's where the stack is. So we take whatever the 8-bit register has, and we add 0, 1 at the beginning, and that's the stack address. But we need to do something with this, right? We need to put that into the status register, except there is a caveat here. If you look at the status register, we see bit 4 and bit 5. They're not the same as everyone else. In particular, bit 5 will always read 0, and bit 4 will usually read 0, but it's not settable by the user. So what we'll do is reg status and this with CF. So we'll clear these 2 bits. And this should get us to cycle 26. Cycle 26 was supposed to read from the stack and didn't. And that was supposed to go into reg PC low. I think we can just do this. So read from the stack. And that should get us to cycle 27. And cycle 27 was supposed to read from 1FF into program counter high. And we got to cycle 28 with unknown command EA. So we actually finished the return from interrupt cycle. Cycle 28 is this one. And that's a very, very, very complicated command, which EA op no operation. Very complicated. Ready? Right. So that's right after LDX. That's it. That's the implementation. It is literally does no operation. Okay, so that got us to cycle 34. Jump subroutine. Oh boy, oh boy, oh boy. Another big one. Let's look at that one. That's a complicated. Unlike no operation, that's an actually complicated one. So jump subroutine. So we go 2-0. Why does it do that? Say 7100, and let's put 00 in. Okay. Jump subroutine. First cycle, fetch the opcode. Second cycle, you already know this. Fetch the next address, which we actually need this time, which is 71, and then do a stack operation, which is a read, but that's just a dummy, because then we do a stack operation that is a write, and we write 00, which is, it's not clear from here, but it's the high part of the program counter. And then we write 102, which is the low part of the program counter. Now you will notice that at this point the program counter is still pointing to the middle of the instruction. So we placed, what we placed on the stack here isn't the return address, it's the return address -1. The reason for that is the 6502 doesn't have enough internal state to be able to store the fetch it already did, the 7.1, and it doesn't have enough internal state to fetch both the high and the low part of the destination address until the end of the command. So it needs to fetch 1. It does have enough internal state to store that. It dumps the program counter to the stack, and then it fetches the other part, and then it can perform the jump. So, and now it reads the high part of the destination, and now we actually jump there. So that's 6 cycles to do a jump subroutine. But the important part is that first, when we write to the stack, we write to the stack after only fetched the first part of the destination address. And what we write to the stack, we write to the stack the program counter while it's still pointing to the middle of the instruction. Those are the important parts because those are the parts that we need to make sure we get right. So, right, so op jump subroutine. Oh, it's the first one. Okay. Jump subroutine and jump subroutine. Run again, and we fail on the same place more or less. So we read this and we read this, but we fail for a different reason. We fail for bus violation. Okay, that's fine. Line 36. Line 36, we were expected to do a stack operation. So, but actually we deviated long before that. So let's start with jump subroutine. So we got here after we've already read the cycle. Yeah, I'm sorry, that's not a stack operation. I just mislabeled it. This is an absolute addressing. Right, the syntax is, we've got jump subroutine, and first of all, it's listed here as an absolute addressing, so obviously I got it wrong. And it has 2 bytes after the command saying, where do we jump to? So it touches the stack, but it's not a stack operation. So the address here will give us the address of the program counter, which we don't need, but that's fine. No, that won't work. I'll show you why. I'll show you why. If we look at what it tries to do, it reads, no, this belongs to the no operation. So the command starts here. It reads the jump subroutine. It reads the low part of the program counter, and it reads the high part of the program counter. But that's wrong. We need to read the low part of the program counter, and then we need to start writing to the stack. So we can't use the standard absolute addressing. We'll need to use the implicit, which means it's on us. and that should work better. So we read right, okay, so we read the opcode, and then we read, no, that doesn't work at all. Okay, no, that should work. Okay, sorry. Yeah, that's fine. Sorry. Okay, so we get this address, and what we need to do, we've already read it once. Yeah, we can't use implicit either. We'll need to use a special. We'll add a special addressing mode here. 0 page, whatever. Okay. So, special goes return PC without doing any bus operations. Cool. This should make it more compatible. Okay, fine. So, what we need to do here is read, but don't store anywhere, except in a local variable, the program counter. So uint 8t dest low equals read program counter. So that's the first two cycles of the opcode. And if we remember here, this cycle, so we did this and we did this, and now we need to start pushing things to the stack. So we go just a dummy read of the stack. And this should get us to cycle 37, 36. The stack pointer is pointing at the wrong place. That means we'd made a mistake before with the RTI. Interesting. I know what the mistake is. We shouldn't have incremented it here. Since the stack pointer points to the free location, and we just freed this location, we should leave it like that. Okay, we got to cycle 37. So we read 1FF, which is good. We go back to JSR. And now we need to push to the stack the low part of the program counter. The low or the high? Let's check that. We need to push to the stack the high part of the program counter. So, write compose reg sp minus minus. We need to decrement it after we get it, and we write there reg pc high. Let's see if that gets us to cycle 38. It did. And now we need to write the low part of the program counter. So that got us to right of the wrong value. Expected 5, got 4. So the address is correct. That's 38. So it expected a write to 1FE of the value 5. Haha. We didn't advance the program counter. See, we got to 40. Okay, so we wrote the right values to the stack. That's cool. And then we read that was supposed to be inside the jump subroutine, but we finished too early. So at this point, we need to go reg PC high equals read of PC and reg PC low equals the value we read before. And that should set us at the correct place to continue execution. Let's see. Yep, unknown command. We are at 40EF, which is where we were supposed to be. Cool. Okay, so at this point, I just git add everything. Okay, almost everything. Okay, next command, PHP, which isn't the programming language by Zend, despite what you might think. PHP. PHP goes like this. The P registers, which is the status register, go into the memory where the stack is pointing, and the stack goes one down. In other words, we push the status register into the stack. Okay, let's see the execution. So that, okay, of course, that's a 08. 08. Where's the program counter right now? Never mind, let's reset. PHP, it goes, first cycle, we read the opcode. Second cycle, we read the byte after the opcode. Nothing new here. Third cycle, we write to the stack the value 71. Sorry, the value 36, which is, what you will notice is that the bits I said we can't handle are set here. So we'll modify that above. And 6 is 0110. That's the interrupt disable and 0 flags. Okay, and then we're on to the next instruction. So 3 cycles. Okay. Void op PHP. And we are at 08. Let's see. We want PHA. The thing is, we're almost identical here. Instead of writing reg A, we write reg status. Except I'm sure you're yelling that at the screen right now. That won't work because we wrote the wrong value. Expected 7.4 got 4.4. The difference between 7.4 and 4.4 is that why does it flicker? Is that these two bits are set. So we made a mistake. We made a mistake before when we pushed data into the reg status. Instead of end with CF, which would clear these two flags bits, what we want is to OR with 3.0, which will set them. But because there are bits that cannot be set, I'll also want to initialize the status register. Okay. We are at 4.3 unknown command. So we finished the PHP command. Cool. What is B0? It's branch carry set. Cool. It's a cool command. Let's see how it works. So first the datasheet. Branch carry set says branch if the carry is set, which is, I don't know, not very helpful. So let's see at how the actual execution goes. So we want, I forgot, B0. B0, and there's only one byte afterwards. So the branch is relative to the program counter. So let's start with 0.2 and see how that goes. So we do branch carry set. The carry currently is clear. So first cycle we read the opcode, second cycle we read the offset, and that's it. We're executing the next command. So that's simple enough. Let's code that. The beauty of working with a very rigid test case that will tell you as soon as you deviate is that you can experiment. That's a wonderful thing. It's a really powerful tool. So we can just go op branch carry set. And I'm going to list this command as ADDR mode immediate. The reason I'm listing it as immediate is because it takes 1 byte that is inline the operand of the opcode. And that's exactly how immediate addressing works. So as far as I'm concerned, it gets me the correct value. It also leaves the program counter in the correct state. So, where were we? Op branch carry set. Goes just read the value. Essentially, as far as we care right now, this is a NOP. But I am going to do some forward thinking in doing this. Branch helper so I'll just do if We had a macros for checking the statuses, right? Here we go. cc get carry branch carry set. No, we'll do this. Branch helper addr. So we give it a boolean that tells us whether we jump. And we know that if the first thing we do is we read the addr. So this should get us, assuming the carry isn't set at this point, which I think, I don't remember. Let's see. No declaration of branch helper. Okay, we can fix that. Branch helper gets addr and boolean (164) missing colon. Right. Okay, unknown command 90. So the branch carry set worked as we expected it to. 90 at 406 F2. So that's a branch carry clear. Okay, the branch carry clear is very simple to implement. It just goes branch carry set and not. Simplicity itself. Branch carry clear. We are at opcode 90, so op branch carry clear addr mode immediate. And we go 70 unknown command branch overflow set. We'll do branch overflow set. And we'll do branch overflow clear while we're at it. So branch overflow set, sorry, here, a 50 is clear and 70 is set. So (50) and 70, and this is overflow. And as for here, we go duplicate that and go overflow, overflow, code reuse or something. And at this point, we should get to, right, the validation failed. We were pretending we're doing a branch and we're not doing a branch. I was waiting for the verification to fail. So, cycle 48, we were supposed to read from 40FF, and instead we read from 40F5. So, we were at branch carry clear. We know that the carry is clear, so that was supposed to jump. And instead, it obviously didn't jump. So let's see how a jump is supposed to look like. So 90 is branch carry clear. Let's run that in the emulator. First cycle, fine. A second cycle, we read the offset. And then we read the next opcode. Let's do a bigger jump. First cycle, second cycle. We read the memory address right after that. Why? Because we need to do an operation. We need to do an ALU operation. We need to add the value we read to the program counter. And that takes a whole cycle at the 6502. So while it is doing that, it's just doing a dummy read from the program counter. And then we jump to where the program counter is currently pointing, which is 2, plus the offset we gave, which is 5 to 7. Cool. That's cool. We can do that. So, branch helper. If jump, reg PC low plus ADDR. Sorry, not ADDR. uint 8t offset equals that's simple enough. Except, like I said, we need a dummy cycle here. So while we do that, we do read PC. So the opcode takes 2 cycles if we're not jumping, and 3 if we are jumping. Sort of. It does get more complicated than that. Like I said, it's an interesting opcode. And on command 30 at 40ff. Okay, so 40ff is branch minus. Branch minus is branch if negative flag is 1. We can do that. And while we're doing that, we can also do branch plus, which is the opposite one. So branch carry clear, branch carry set. Let's sort these so that branch minus is if the negative is set, and branch plus is if the negative is clear. And they are at branch minus is 30. And branch plus is at 10. Okay. Unknown command at 41F4. I have to admit it got a lot further than I thought it would. 41F4. We're not actually executing this. Okay, so let's discuss what we're getting wrong here. We're actually getting 2 things wrong here. The first is that the branch doesn't have to jump forward. It can also jump backwards. So so here's the thing. When we look at the branch helper, which we had somewhere, we can do that by just setting the putting the offset not into an unsigned 8-bit value but into a signed 8-bit value. Sadly, this doesn't generate a warning. It really should have, but it doesn't. C++ doesn't protect you from this type of casts, so it just compiles. But that's not all, because here's the thing. I'll demonstrate that. So instead of 0.5, let's do here F0. So we're supposed to jump 16 bytes backwards. But what you'll notice is that if we need to jump 16 bytes backwards, we are crossing a page, which means we need to update not only the low part of the program counter, but also the high part of the program counter. Problem is, the CPU calculates where we jump to using the ALU, which is an 8-bit ALU. It doesn't know how to do 16-bit calculations. So the CPU needs an extra cycle to process this case. So first cycle, we read the opcode. Second cycle, we read the next instruction. Third cycle, we do a dummy cycle to calculate where we're going. And then in the fourth cycle, we're reading from something which looks completely random. It looks like unrelated to anything at all. And in the next cycle, we're reading from the correct address. But now we see that this wasn't a random address after all. This is the correct low, PC low, the correct program counter low part byte with the current program counter high byte. So it takes another cycle to run another ALU operation to calculate the update to the high part of the program counter. And while it does that, it reads from an address which is effectively random. Now, I'll note that this datasheet belongs to the Western Design Center 65C02, which is a much later CPU. And one of the things they're particularly proud of is that they fixed those bugs. So this CPU, the datasheet for which the CPU is, doesn't do that. I don't remember where it reads from in that extra cycle. But we don't care. We're implementing the MOS 6502. So what we're going to do is this. We're going to create uint 16 value, which is the program counter. And then we go program counter plus offset. So that gives us the correct value, which is not what we want, ironically enough. So we go reg PC low equals program counter and FF. So we truncate the low byte and we put that where we need it. And then we test whether we cross the page, which is simple to do here. When you do with actual 8-bit arithmetic, it's more complicated. So we do is reg program counter high equal to program counter shifted right by 8 bits. If it's not equal, if it's equal, we're done. If it's not equal, we do another dummy read from a program counter, which is now pointing to this strange hybrid, right? Because we've updated the low part, we haven't updated the high part yet. And then we can finally go update the high part with a shift. I think I scrambled things here a little. Okay, here goes. And that should finally implement the branch instruction the way the 6502 does that. So, and we see that because we stopped complaining about invalid commands. Zero is a command that shouldn't have been executed. D0 is a command that should be executed. All the branch instructions in the 6502 have an odd higher number and a zero lower number. So let's just finish that one. D0 at a 4AFB, 40FB. That's branch not equal. Let's handle those real quick. Not equal and branch equal. Case D0 op branch not equal. And branch equal. Alphabetically, it needs to go after branch carry set. So branch equal means that the zero flag is set. The origin of this is that when you do a compare, you're actually subtracting the two numbers, and if the result is zero, it means they're the same. So it's a bit of a strange naming, but yeah. And branch not equal means that the zero flag is clear. Duplicate case value. Yes, they are right. They are absolutely right. Branch equal is F0. And we got to 40F8. By the way, I'll take a vote if you want to stop now. Just write in the comments how much longer you want to go. We have reached 60 cycles into the execution, which is not bad, but we're not close to getting it done. So tell me what you think. That's a jump. A jump should be easy. Ready for a jump? C, jump. 4C 2048. Okay, so a jump goes like this. First cycle, we read the data, and then 2 more cycles to read the address, and then we just jump them. Surprisingly straightforward. So, void op jump addr. And here we go case 4C op jump addr mode absolute. And it goes really, really simple. It goes reg PC low equals addr and ff. Reg PC high equals addr shifted by 8-bit. That's it. You know why? because everything was handled by the addressing mode. It already read the 2 bytes and figured out where they were. So we've not only got the address we were jumping to, we also consume the correct number of cycles in doing so. Which brings us to 4103, which is PLP. PLP is, why should I tell you what it is? We can show you what it is. PLP is pulling the status flag, the P register, from the stack. So we go stack +1 to stack and memory stack to P. And then it affects all of those, except it doesn't affect this one. They're lying. It doesn't. I think we can actually see that in the test plan. We go, let's see which cycle we were on, 63. So we go pull P, and then we read back 7-4. So no, we're not seeing that. But we're not affecting the B flag. There is only one place we can affect the B flag. We'll do PLP and RTS, and then we'll be done for today. Shouldn't take long. Okay, so op PLP. We're pretty much copying op PLA. We read the address. That's the dummy stack cycle we're doing because the stack pointer isn't pointing to the correct place. And then we're adding 1 to the stack pointer. We're reading the value again, but this time into the status register. And we're ORing it with 30 as before. And obviously we're not affecting the flags otherwise. Case PLP is 28. Let's see if that passes. We were at 63 and now we are at 67. Yes, that is correct. 67 is RTS, which stands for return from subroutine. That's another slightly complicated instruction. So let's just read it in first. RTS and we want to edit ADDR mode stack. That should work. Let's see. Yep. RTS. Sorry about that. Okay. So let's see how RTS actually works. So we write there 60 and we reset. Okay, so first cycle we read the opcode, second cycle we read the next byte because we haven't analyzed the opcode yet, and then we read the stack, but that's the wrong address because that's the free location. So we use that cycle in order to increase the stack pointer by 1, and then we read the stack from the correct address, and that gives us FF, and then 1-3, and then we execute sorry, we read for 13FF. But that's not executing a command. We then go to 1400, and that's executing a command. So 1, 2, 3, 4, 5, 6. Why do we do that? We do that because we don't have a 16-bit ALU, but we do have a component that can add 1 to a 16-bit value. That's inside the program counter. So if you'll remember, when we did jump subroutine, we were writing a program counter that is by 1 too low. So first we load the value from the stack into the program counter, and then we use this cycle to increment the program counter by 1 as usual. So that's the way we do the increment by 1. That's the way the 6502 does that. So let's see what we already have from those. We need 6 cycles altogether. We get to cycle 69, which means that we did this. We did the first cycle of fetching the opcode. We did this, the second cycle of fetching the value. And this cycle we already went off track. So what we need is a reg PC high equals. So sorry, first of all, we need a dummy read from the stack. A dummy read will look like this. And then we want an actual read from the stack into the PC high, into the first read is into the PC low. Into the PC low. And then we need another read into the PC high, at which point we do not increment the stack pointer because we're done. And now, so that's third cycle, fourth cycle, fifth cycle. And then we go read from program counter and advance program counter. And indeed, we see that we started with a program counter at 4104. We read 1, 5, and 3 from the stack, and we're reading from 315, and we're executing from 316. That's cycle 199. Actually, we got quite a lot further at this point. We advanced quite a lot. We made a pretty big jump because we returned to opcodes we already implemented. And so we're executing A0 which is load Y. We did the load X, and that apparently worked. Okay, I think that's a good place to stop. We will continue with this next week. Thank you for joining me live. Really appreciate it. See you next week, I hope.